Welcome to Section 4 of Biostatistics. As a reminder, we can think of biostatistics in three arms: performing the study, evaluating the study, and applying the study clinically. In this lecture, we are still focused on evaluating the studies, and we will do this by studying statistical tests. So let's get started. Now, statistical tests are fairly straightforward, and your most important task is to determine when to use which test. The basic idea of statistical tests are to take the data that you got from your study and determine if your results are statistically significant. Recall that you determine that a test is statistically significant if your p-value is less than 0.05. Recall our mnemonic beta power and alpha p. Anytime we accept the alternative hypothesis, H1, we think of our alpha or p-value. So this is what we're referring to here. A p-value less than 0.05 is statistically significant. The important statistical tests you need to know are written below. We have two-sample t-test, the analysis of variance test, or ANOVA, chi-square tests, correlation coefficients, and meta-analyses. The two-sample t-test is very simple. It compares the means of two groups, and you use a two-sample t-test when you are studying numerical data. Now let's say we have two samples or groups. Group A has an average LDL level of 65 milligrams per deciliter, while Group B has an average LDL level of 58 milligrams per deciliter. With these two groups, you can perform a two-sample t-test. After all, you are comparing the means of two groups, and this will produce a p-value. The next test is the analysis of variance, or ANOVA test, and this compares the means of two or more groups. Otherwise, it's exactly the same as a two-sample t-test. Therefore, you use the ANOVA test for numerical data. When we discussed the two-sample t-test, we had two groups, A and B. Group A had an average LDL level of 65 milligrams per deciliter, while Group B had an average LDL level of 58 milligrams per deciliter. But now let's say you have a third group, Group C, and this group has an average LDL level of 51 milligrams per deciliter. In this case, instead of using a two-sample t-test, you will use a ANOVA test. After all, you are comparing the means of two or more groups, in this case three groups. And as always, this will produce a p-value. And this p-value will tell you if it's statistically significant. And just to tie it back, if you have these three different groups and you claim that they are all different, which means you accept the alternative hypothesis, H1, and recall from our mnemonic, beta power and alpha p, whenever you accept the alternative hypothesis, which we did, we think of our alpha error and our p-value. Now let's talk about chi-square tests. Chi-square tests can find associations, and they are used for categorical data, as opposed to the numerical data you use for two-sample t-tests and ANOVA tests. Identifying numerical data is fairly straightforward and intuitive, but sometimes it can be confusing to know when you're looking at categorical data. So I've listed some examples here. We have age, gender, race. Those would be considered categories. A treated group or a not treated group, those would also be considered categories. If study participants are placed in a high or a low results group, that's considered categorical. Frequently, percentages are used for categorical data. For example, 35% of heavy smokers. Being a heavy smoker is categorical, even though 35% appears to be numerical data. Just don't get tripped up on that. And we'll make this perfectly clear on a new slide. An example of a chi-square test would be taking the LDL levels and splitting them into categories. For example, we could say that category A includes LDL levels above 70, while category B includes LDL levels that range between 50 and 69. Now clearly, your LDL level is numerical data. We've written that. So I'm going to show you a foolproof way to always determine if you need to use a chi-square test, even if it looks like you should be using a two-sample t-test or an ANOVA test. The trick is by mentally picturing or actually drawing out a 2x2 table. We will put both of our categories on top, so greater than 70 and between 50 and 69. And then we will add two more variables on the left, such as exercise and no exercise. Now let's say that your hypothesis is that people who exercise have LDL levels in this range. You can find that potential association with this table, or you may find that people who do not exercise have an LDL level above 70. Either way, you have set everything up into categories, so any data that you obtain, even if it is a number, such as an LDL level, you will place the data into a category. So let's do a question to apply this. The serum testosterone level of 150 males between the ages of 30 to 69 were measured. The males were broken into two groups based on their age. Ages of the first group ranged from 30 to 49, and ages of the second group ranged from 50 to 69. What test would best evaluate the averages of both groups? So in Group A, the ages ranged from 30 to 49, while Group B had ages ranging from 50 to 69. And then the testosterone level was measured in each group. The three tests we should be thinking about are the two-sample t-test, the ANOVA test, or the chi-square test. So let's first ask if it could be the chi-square test. Well, it couldn't be this one because testosterone is not measured as a categorical variable that can be boxed up. So if we make our 2x2 table, we have two groups. We have 30 to 49-year-olds, and then we have 50 to 69-year-olds, and those are good categorical data. However, our testosterone level cannot be neatly boxed up into one of these categories because testosterone level is a continuous variable with any number of results. However, if the study broke testosterone level down into high and low testosterone, this would fit neatly into a 2x2 table like this. But this is not the case in this situation, so we are not thinking about a chi-square test. Furthermore, in the question, we are asked about evaluating the averages or means of both groups. And whenever you see averages, you should be thinking of two-sample t-test or the ANOVA test. So if it's down to these two, we can just ask, how many groups did we evaluate? We evaluated 2. That means the two-sample t-test is best. Now let's talk about the correlation coefficients. A correlation coefficient will evaluate the relationship or correlation between two variables. And in correlation coefficients, the range is always from -1 to +1. The direction of the relationship is determined by positive or negative, and the strength is determined by the numerical value, ranging from 0 to 1. Correlation coefficients are often demonstrated on scatter plots. Let's say we are evaluating the correlation between body mass index, or BMI, and systolic blood pressure. And we can compare these against each other with BMI on the y-axis and systolic blood pressure on the x-axis. And let's say that as BMI increases, systolic blood pressure increases. That means there would be a line that looks like this. And recall that the correlation coefficient depends on two things: the direction of the relationship and the strength of the relationship. In this case, as we see that BMI increases, so does systolic blood pressure. That means there is a positive relationship. So that gives us the direction. And the strength of the relationship ranges between 0 and 1, and it depends on the scatter around this line. So let's show the scatter of data points here. Now let's draw another graph with less scatter. The graph on the left indicates that systolic blood pressure is impacted by factors other than BMI, which we know is the case. But with all this scatter, the strength would be closer to 0 than to 1. It's obviously not 0, but it's closer to 0 than our comparison graph, which indicates a 1-to-1 relationship, indicating that BMI is the only thing that impacts systolic blood pressure, which of course we know is not the case, but this is how the graph would look if that were the case. So the strength on this right graph is closer to 1. So now let's see what the graph would look like if the data points went in the opposite direction. We can see from these two lower graphs that the direction is negative, indicating that as BMI increases, systolic blood pressure decreases. Let's once again determine the strength of the relationship by looking at scatter. So once again, the strength of the relationship ranges between 0 and 1, and the graph on the left indicates lower strength. In other words, there are things other than BMI that decrease systolic blood pressure, so the relationship would be closer to 0 than the one on the right graph, and the one on the right would be closer to 1. Another simple way of reviewing correlation coefficients is by looking at the spectrum from -1 to +1 on the x-axis, with 0 in the middle. Notice the positive association as we move up and right. Also notice the decreased scatter as you increase from +0.5 to +1. This indicates a stronger relationship. And the same is true with the negative side of the graph. A good rule of thumb is to think of any R or correlation coefficient greater than 0.5 in either direction as being strong, while anything in between is weak. Now let's do a question to apply this. Let's say a study finds that higher use of cigarettes decreased the incidence of uterine cancer in postmenopausal women. Researchers also found that most cancer-free women did not smoke. What is the likely strength and direction of the correlation coefficient? So the study found that higher tobacco use was associated with lower incidence of uterine cancer. So if we plot this out on the graph, it would look like this. The question stem states that as tobacco use increases, uterine cancer incidence decreases. So the direction would look like this. This is a negative correlation. Now let's find the strength of the relationship. Now the question stem actually told us the strength of the relationship. It was just kind of cryptic. What I'm referring to is when the question stem states that researchers found that most cancer-free women did not smoke. This is a huge point, and it is very important you know what to do with this information. If many women without uterine cancer are non-smokers, then there must be other things that contribute to decreased uterine cancer other than tobacco. In other words, we have uterine cancer. We found a negative relationship between increasing tobacco use and lower uterine cancer. However, most of our patients with decreased uterine cancer incidence actually didn't smoke. So there are other factors at work. That means the strength of this relationship is closer to 0. That means our scatter would be rather great. So if we were to categorize our strength, it would be somewhere between 0 and 5, or the weaker side. The last thing we need to talk about are meta-analyses. In these studies, researchers will analyze the pooled data of many studies. All of this collective data gives us a very higher sample size. In other words, a big N. This gives us higher statistical power. And recall that whenever you think of statistical power, you should think of low beta because of the equation power equals 1 minus beta. And that concludes this section.